I am so delighted to welcome our speaker, Rutuja. Rutuja Dhanawade is a graduate student at Northeastern University studying data analytics with a specialization in machine learning. During her research and assistantship at Northeastern University, she focused on NLP, or natural language processing, and recommendation systems. And prior to her academic pursuits, she worked as a data scientist at Larson and Turbo Infotech. Her workshop today is entitled Natural Language Processing, Sentiment Analysis of Customer Reviews Using Transformers, parentheses, BERT. So without further ado, please welcome Rutuja.
Hi, everyone. Good morning, good afternoon from wherever you are. And thank you so much, Laura, to introduce me and giving me this opportunity. I'm very excited to come up with today's session. Let me just share the screen. Can you just confirm if the screen is visible?
It is visible, but if you hit slideshow, yes, perfect. That looks great.
That's great. So, yeah, as Laura mentioned, I'm a graduate student at Northeastern University, and during my research assistantship, I got a chance to work on lots of NLP data, where I even developed learning modules on natural language processing. And directly straight away hitting to our today's topic, let's get started with the sentiment analysis for customer reviews using transformers. So with the advent of e-commerce and social media, there are a lot of textual reviews and textual data being generated. And the challenge is to analyze or perform data mining tasks on this textual data. So as we all know, since the advent of Chat GPT, there are a lot of things coming up with the transformers, working of transformers. So I thought, let's dive into the working of transformers and getting a high level overview for the same. So I would just like to ask every one of you, you can just put up in the chat box, how many of you are familiar with the basics of neural networks, or have you heard like recurrent neural networks or LSTM? Feel free to drop in the chat box like yes or no, or are you at a beginner level? And then we can continue. Yeah, I can like take a minute for the same, and yeah. Okay, so I can see we have a mixed crowd. Yes, beginner. Okay, there's someone saying please explain from scratch. Definitely, I'll try to do that. Okay, got it. So thank you for the response, and moving ahead. So basics of neural networks. So basically it's a multi-layer perceptron where you have the input data and the weights are multiplied to the input, so that there is a neuron in it, and then it passes through the activation function. So this recurrent neural networks is a special case of basic neural networks, and is usually used to process sequential data. So when you have time series data or textual data, before the advent of transformers, before Chat GPT or before BERT model, back in 2017 or 18, it was neural networks and recurrent neural networks and LSTM models, which perform the text processing and text classification for us. So as you can see here, this is an example of recurrent neural network. And what happens in a recurrent neural networks is at each timestamp, one input word is passed, and the previous output from the previous hidden state is also passed, fed into the neuron. So this is how the recurrent neural networks takes care of the sequential data, and it remembers the word just prior to the current word. And the reason it is important to understand the recurrent neural networks or neural networks basics is that the heavy or complex models like the transformer model or the BERT model or the Chat GPT model are based on this basic architecture of recurrent neural networks or LSTMs, and so on. So moving ahead with our slides. Yeah. Just adjust this. Okay. So here, to explain it in an easy to understand manner, I have created an analogy of a house, and the way a house is built right from scratch, from bricks, then multiple bricks come together to form wall, and then we have the room and then the bungalow. So similarly, the perceptron, basic neural network, is used to create a recurrent neural network. And then when we combine multiple neural networks or like the GRUs or LSTM. LSTM is long short-term memory, which is another neural network architecture also used for processing sequential data like text data and time series data. So when we have multiple blocks of such small recurrent neural network and LSTM models, we have an encoder and decoder model. So the interesting thing about encoder and decoders is that initially it was invented to perform the task of language translation. So what the encoder blocks does is it takes in the input text. Every text is represented in the small separate words, and then these tokens are represented into numeric form. All these tasks are done by the recurrent neural networks. And then the task of the decoder, in simple words, is to regenerate and translate the numeric embeddings into another language. Let's say, for example, you have a German text being passed into the encoder. So the encoder will take up the German text, break it into small words, and each word will be represented in a numeric form by the encoder. And once the numbers are represented, the decoder will take this input and translate it way back to English language. So this is another example of supervised learning, and encoder decoders were initially started for language translation. So moving ahead, then there came an era of transformers around 2018, when the researchers found that when you stack up multiple encoder and decoder layers, you can make the machine learning model do great sorts like not only language translation, but next sentence prediction or language generation or text classification and so on. So here, as we can see, when multiple encoder or decoder blocks are combined, we have something known as transformers. And then basically the transformers are the building blocks, or the the transformers are the major chunk in the BERT model or Chat GPT. There are many variants, and various companies have their own models, like Google has BERT, Facebook has the BART model, or the OpenAI has the Chat GPT model. So the crux of all these variants of transformers are the encoder, decoders, and the transformer architecture. So let's dive into the transformers architecture. So if you have taken an NLP course or in any way are familiar with the NLP, natural language processing, any of the things, then you might have heard something called as attention is all you need. This was the paper released in 2018, which explained about the transformer architecture. So what highlights an transformer architecture differently than other text processing areas such as the bag of words or TF-IDF vectors? There are various different methods by which you can convert the text data into numeric form. So if you know the bag of words, TF-IDF, all these methods are also some of the other ways in which you can convert the textual data into numbers. But what transformer does differently than all these other methods is it grabs the context of the word as well. So for an example, if you can see these two sentences, I need to deposit money in the bank, and animals gathered near the river bank to drink water. So the word bank has different meanings in both the sentences. As humans, we understand that this meaning is different, but before transformers, it was difficult to train the model and make it understand the context of the surrounding words. So the encoder and decoder blocks in the transformer have this interesting feature of self-attention. And this is what helps the model to understand the context of the word. So whenever the word bank would be represented in a numeric form, the number would take into consideration the context of its previous and the next word. As a result, the word bank will have different type of numeric representation for the first sentence, and it would have different kind of representation, a different number for the second sentence. And how does transformer does this is using the key query key value pair, which is a complex matrix multiplication, and it is a little difficult to cover in this given scope of this lecture. But that's how the transformers make sure that every word is represented along with the context in which the sentence is being used. So that's all about transformers. And as I mentioned previously, so just the transformer is the base for all the various types of large language models which we have, like the BERT, be it ChatGPT or GPT-3, or be it any other large language model. So yeah, coming back to the BERT transformer, here we can see we can brush roughly through the BERT architecture. And if you remember from the second slide, we learned that when you stack up multiple encoder or decoders, we get a transformer. So in the BERT is made of only 12 encoder stacks. It doesn't have a decoder stack, and hence it is said to be it's not a sequence to sequence model. So sequence to sequence model is somewhere when you have the encoder stacks as well as equal number of decoder stacks, and mostly they are used for language translation. So Facebook's BART model is one of that type, where it has both the encoder and the decoder representation. And that's how the name of BERT is. It stands for bidirectional encoder representation from the transformers. So the word bidirectional ensures that the BERT understands the input data from both the directions, and as we saw in the previous example, the word bank would take into consideration the previous words as well as the preceding words come after that. So there are different architectures of BERT. One of them is BERT base and BERT large. And I would highly suggest that if you're more interested to know about BERT architecture and understanding about transformers, then you can explore this blog by Jay Alamar, and he has explained in various ways and very intuitive ways how the BERT encoder works. Another one variant of BERT is also DistilBERT. There are actually many, like DistilBERT, Roberta, and all. So the way these models are trained is different in each of the variants. Some of them are easy and lightweight, just like the DistilBERT. So the DistilBERT, which also we would be learning in the code notebook, has only 6 encoder stacks. So it has just like the BERT base has 12 encoder stacks, one after other. It has only 6 encoder stacks, and yet it retains 97% of the performance of the BERT. So DistilBERT is light and very easy to use, and I mean, it's easier to train than BERT. And initially, BERT was trained on huge corpus of like hundreds of millions of words, and the number of parameters on which it was trained is huge. There are almost like 60 million more than 60 million parameters, which required the BERT model to be trained, and that takes a huge amount of time. So from there came a concept of transfer learning, where we have these pre-trained models, and we can just use those models to feed our data and perform a different task. So that is what also we are going to explore in the code notebook. And before moving ahead, it is very interesting to understand how the BERT model was trained. So the BERT model was basically trained on it was trained on two main tasks. One of them was the masked language modeling. So in this masked language modeling, what happens is, for example, just consider as a student, or if you're learning some new language, then we often have this kind of questions like fill in the blank or write the appropriate word in the blank. So similarly, just like that, BERT was also trained by skipping few of the words in the input sequence. So if you see in this example, the input sequence, how are dash, that is mask, doing? And the target sequence was also fed to it saying, how are you doing? So what the objective of this training task was, the BERT should understand which word should be placed in the mask sentence. So mask is something which was not fed, the word at that position was not fed to the BERT model, but it was asked to predict it. And while training, around 15 to like 12 to 15% of the tokens were masked. That was, they were placed with a blank. And that's how the BERT was trained for the masked language modeling task. And simultaneously, the BERT was also trained for the next sentence prediction task. What happens in the next sentence prediction task is that there are two input sequences fed to the model, where the first sentence, as you can see here, is, for example, the man dash to the store, for example. And the second sentence is penguin dash is our flightless birds. So here what happens is the two sentences, as you can see, are not related to each other. And the second sentence B, is not the appropriate next sentence for the first sentence. So while training, 50% of the training samples consisted of sentence A, a pair of sentence A and B, where the second sentence was not exactly the following up sentence. And 50% of the data included a pair of sentence A and B, where the second sentence was actually the following sentence to the first one. So this is basically a binary classification problem, where the model is trained to identify whether the second sentence is actually ideal next sentence for the first sentence or not. What the outcome of this task was, it helped the BERT model to understand the contextual meaning. Meaning, are the two sentences related to each other, or they're randomly placed? So the target is next or is not next. So let's say, for example, if you passed a pair of two sentences which are actually related to each other, then the prediction would be is next would be yes, or is not next would have been no, in case you just passed randomly two sentences to the BERT model. So these were the two tasks on which BERT was trained, and it was simultaneously trained. So and now what we can do is there are many different ways and variants of BERT model which we can pick up from the Hugging Face library and train them and fine-tune them according to our data, and use it to perform any task which we want related to natural language processing. So here is another thing which BERT also does, is it has the BERT Tokenizer. So as we all know, the embeddings, that means the input is represented in the form of numeric form for each of the tokens. And this tokenizer library is the BERT takes care of the tokenization process as well. So if you're not familiar with tokenization, what tokenization means is the process of dividing the input sentence into different words and representing it into a numeric form. So the interesting thing and what the BERT tokenizer or the transformer model does is that it also includes the position information about the position of the word, and that also helps it to have the context of the sentence or the word. So as you can see, for example, this input sentence, my dog is cute and he likes playing. So this is the input a layman would feed into the model. What the BERT tokenizer would do is firstly divide it into small words, and then it is represented in a numeric form. And not only this, the sentence embedding, as you can see, it makes sure to indicate the BERT model that whether the sentence belongs to the first sentence or whether the text or the token belongs to the second sentence. So that is what this information is also passed to the BERT model through this BERT tokenizer. And lastly, as we can see, the transformer position embedding. So here you can see E0, E1, E2 up to E10. So again, this is a numeric representation, and to calculate the position of a particular word, this formula is used, where if the word is even, then you use the first formula, which is sine of the position upon 1000 raised to 2i. And if the position, the word is placed at the odd position, then we have the second formula with the cos. So as a result of this, the tokenization process not only includes the input IDs, but it also includes the position information, which again, as I mentioned before, helps the model to understand context of particular word with the surrounding words in the given sentence. Now, moving ahead, and we got an overview of how BERT model works and how transformers can be used to process textual data. We can explore how there are various ways of tuning models, and we might not have to train these models from scratch, as they are readily available on various frameworks like the Hugging Face framework or the OpenAI framework. So moving ahead from this slide, it's not just related to BERT, but these types of tuning can be applied to any of the models. So we begin with the zero-shot classification method. In this type of classification, what zero-shot classification means is you don't need any input training data. Like, even if you don't have any input data, then you can straight away go to the transformers library, import this pipeline, as you can see in the image, and choose whichever model you need. For example, in this photo picture, as you can see, the model is Facebook BART large mini. So once you pass whatever the task you have to perform into the pipeline, it does the work for you. So I mean, just to consider as an example, if you see here, I have a problem with my iPhone that needs to be resolved ASAP. So this is my input text, and the candidate labels which I wish to classify this text into also would be passed. And it says urgent, non-urgent, phone, tablet, or computer. So when you pass this set of input and expected output target variables, what the model will provide you is with the labels and the score. So as we all can understand, the sentence is focusing on urgency and covers the phone. It's not a tablet or computer. So you can see the model has given 0.5 score. That's the probability of being urgent, and the probability that this input is talking about a phone is 0.747. Sorry. So This is a type of zero-shot classification. And as I mentioned in this, you can take away readily available pre-trained models and use it for any data and perform any task which you need. So if you want to explore more about zero-shot classification, then I would recommend you can explore this reference and Hugging Face zero-shot classification library, and you can use it for any purpose, even if the data set or your task is different than what the model was trained on. So this is the first type. Moving ahead, the second one is few-shot learning. So what happens in few-shot learning is you need to provide the model at least a couple of training examples, like 3 or 4 examples. And then once it understands what the model has to do, it can predict well on your input data. So again, in this type, there is no need to train the models or train the weights or run the pre-train. There's no need to tune any weights or change the weights, existing weights of the model. It's just that you are readily using the pre-trained model and supplying it with sample data set, which sample training records according to the prompts. So if we come back to our example of like sentiment analysis, then you can see importing from this NLP cloud client, here is the example of GPT-J, which can do the work of fine-tuning with like very few training examples, only 3 or 4 are enough. So if you see in this example, as the input says, you just need to pass the message. For example, the support has been terrible for 2 weeks and the sentiment is negative. So this is what we pass to the model for it to understand that, okay, you have to classify this sentence as negative because it's because it's like a complaint. The next example you pass it to it is the I love your API. It is simple and so fast. The sentiment associated with this positive. And the third is an example for neutral, which says GPT-J has been released 2 months ago. So once you give example of sample trainings records what you want, it understands, and then here at the fourth step, you can pass your new input text which you want to be which you want the model to predict. For example, the reactivity of your team has been amazing. Thanks. So if you want, for example, this is your test data point and you want to know what sentiment it says, then here you can see it has easily predicted positive. So this kind of few shot learning can be used when you have very less data and where there's no much of computational resources availability, and you won't need like to train or even fine tune a model in this type of approach. And as I mentioned, if you want to explore more, then here is the link for same, and you can see how the few shot learning with GPT works from this link. And lastly, we have the fine tuning, which is also what we are going to learn and have a look in the code notebook. So fine tuning refers to the process of adapting a pre-trained model to do a specific task. And in this approach, there's a chance that you make slight adjustments to the weights and then train it on your input data. And it is recommended to have at least 200 training samples when you go for this approach of fine-tuning a model. And so as you can see in this example, there's this blog and it shows how you can fine-tune a GPT-3 model. So you just need to prepare data in the given format ready to be fed to the model. Just as we saw in the BERT, we need to prepare data using the BERT Tokenizer. For GPT, it needs the data in a JSON file. So that can be done. And within like few minutes of training, you can have it pre-trained and customized to your own custom data set. So that was about various types of fine-tuning. And moving ahead, we can now go to the implementation of sentiment analysis of customer reviews, which is a code walkthrough of the case study. And for this, we are going to use the DistilBERT model, which is a variant of BERT model, and it is 40% faster, and it retains the performance as we saw to up to 97% in the BERT model. So here is the link to the code notebook, and the data set is the Amazon Alexa reviews data set, which is available on Kaggle. So if you want to walk through the code notebook along with me, then you can follow up, or or else you can just learn with me right now and try running the model later. It might take like 15 to 20 minutes to train the model, because since DistilBERT is a heavy model and we are training it, we are doing the fine tuning. So we would be changing the parameters and it takes time. So the first step is to install the TensorFlow transformers library. And the interesting part about this transformers library is the Hugging Face interface is a framework which provides you a wide variety of models, which I can also show you here. So if you want to explore, you can just go to Hugging Face and see all these various types of large language models. And we have like DistilBERT, we have GPT. So all this models can be inculcated in your code. So just like for machine learning models, we have scikit-learn. For deep learning and large language models, we have this transformers library. And here is a set of libraries you need to import. Since we are using the DistilBERT, we need DistilBERT Tokenizer for processing the input, and DistilBERT for sequence classification. Now we are using sequence classification because we want to do the sentiment analysis and classify the review as positive or negative. So if you want to perform any other task like text summarization or text generation, then there are different variety of libraries available for those tasks. And yeah, so I hope everyone is familiar with the Google Colab. If not, you can just drop your doubts in the Q&A or chat section, and towards the end of the session, we can discuss over it. So one important step I will suggest every one of you to do while running the code notebook is go to the runtime and change the runtime to GPU. What this will do is it will allow you to access the GPU functionality for the Google Colab, which allows the multi-core processing and helps in reducing the training time of the model. So once you save it, you can see it says connect to GPU. And then the first step, as we see here, is the loading the data set. In this code notebook as well, I've mentioned the link to the data set and the link to the presentation earlier, which we saw. So here we can see that given data set is in the TSV form. What a TSV form is, it's basically instead of being comma separated form, it's separated by the tabs. So when we read the data set, we need to pass the separator as /t, which will indicate that the data set is data is separated with the tabs. And when we load the data set and we can have a look over the first 5 rows, we can see, or when the review is love my echo, the feedback or the sentiment is 1. Similarly, here is another example where the reviews is like very negative and the feedback or the sentiment we can say is 0. So One important step always before you go with any machine learning model, or especially for classification, is to check whether the data is balanced or not. And very often it happens that there is a lot of class imbalance, and the choice of our target variable. For example, depending on the business scenario, if the business owner wants to focus on negative reviews for which kind of products are we getting more negative reviews, then the class of interest, our class of interest would be negative reviews. But in reality, if we see, and as seen in this data set as well, we have very less number of zero or negative reviews, and we have large number of positive reviews. So one important step is to balance the data. And for this, also this can indicate that, so yeah, one insight you can infer from this is maybe people do not tend to give negative reviews, or people are not very friendly or comfortable sharing negative reviews. This is one point which indicates. And maybe another point of view is that a certain product might not have many negative reviews. So these are the challenges you face while working in real life data, because right now we are taking a data set from Kaggle and implementing, but when you are actually working on real life data, there are a lot of things which matter and need to be taken care of during the pre-processing step. So to deal with this class imbalance issue, we would be undersampling. So there are two methods. One is undersampling and oversampling. In undersampling, what you can do is, now in our case, the majority class is with the value 1, because we have a lot of training samples with feedback equal to 1. So what we can do is, in undersampling, we can take only those number of variables which are equal to the negative reviews. So we have only 257 negative reviews. Then what we do in undersampling is, out of these 2,800 positive reviews, we randomly select only 257 negative reviews, so that it matches with the data set is balanced. It matches with the number of negative reviews. And another example, another method of dealing with this issue is oversampling. So in oversampling, what we do is we get multiple copies or repeat the training samples in the data in the class which is minor. So let's say in our example, we would have to repeat the data present in this feedback equal to 0 class and maybe create multiple copies. But since we are dealing with the textual data, we go with the undersampling approach. And as we are fine-tuning BERT model, and it's fine even if you have like few like 200 or 300 of training sample, even then that's fine. We have like these set of transformer models which can be fine-tuned with like very little available data. So the next thing we do is create a balanced data set. And here what we do is we create a negative data frame having only negative reviews. And out of those negative reviews, we randomly select 257. We create a data set of negative reviews and positive reviews. And as we have a lot of positive reviews, we randomly select 257, which is also the number of records in the negative samples. And we create a data frame which is balanced. So at the end, our final balanced data set will have 257 positive reviews and 257 negative reviews, which makes to a final shape of 514 records in our data set. And we can see that again, the feedback is now, our data set is now balanced. Yeah. So moving ahead, another important task which we should do during working on text data is analyze the length of reviews. So in real life, some reviews are too long, some reviews are too short. So I'll quickly glance over this and this your whatever reviews we have calculated the length of those reviews and plotted a histogram. This shows that mostly the maximum length is around 50 for our reviews. There might be 1 or 2 reviews which go till like 200 or have 200 or 300 words, but we won't consider that. So this is important step because it helps us to decide a parameter called maximum length while tuning the DistilBERT model. So just remember for our data set, as it has the maximum of 50 reviews, 50 words in all the reviews, we'll have the max length of 50. So yeah, moving ahead. Now is the time to process data with the DistilBERT tokenizer. So what the DistilBERT tokenizer does is, from this diagram you can understand, it divides the word sentence into individual tokens, and it adds a CLS and SCP token. So these two tokens indicate the start and the end of the sentence respectively. So once the CLS and separated token are added, it converts all the input tokens into its numeric representation. So just to give you an idea of how this is done, we can take an example of this review, which says the best thing I ever I have invested in a while, and thank you so much. So as you can see, it does have these emojis as well, and it's interesting to see how the BERT tokenizer processes these emojis as well. So what you need to pass to the BERT tokenizer is the BERT model name, which is in our case the DistilBERT base uncased model. And here comes the maximum length, which we have set to 50 because our reviews can have maximum number of words up to 50. And this truncation equal to true parameter makes sure that any input text beyond 50 would be truncated, because we barely have any reviews which go beyond the length of 50 words. So yeah, and the padding equal to max length. So what padding does is, there are instances where not all the reviews have long like 50 words. So and in such, for example, if a review has just 2 words, so for the remaining 48 words, what it will do is it will pad with the 0 symbol. And you can see if we tokenize this using the BERT tokenizer, what output we get is as the above diagram we saw, the tokens are generated. And it's interesting to see how it also took care of I have. It separated the 2 words. And for the emojis, it added a UNK, which indicates an unknown symbol. So when these are converted into numbers, the BERT tokenizer calls it input IDs. And you can see the 101 is for the CLS token, and the ending 102 is for the separated token. And in between all these words, all the other words are represented using these numbers. One important thing for the BERT or DistilBERT model is attention mask. So what attention mask array does is it adds an array of either ones or zeros, where 1 indicates that the corresponding word in the input ID is a valid word, and 0 is mentioned for the padded word. So you can see all the words which are represented by 0 in the input IDs have 0 value in the attention mask as well. So attention mask indicates the model that which input tokens the model should pay attention to, and which are just like for the sake of padding, and those input tokens can be ignored by the model. So that's the task of attention mask. And then the next step in our preprocessing is creating the TensorFlow data set. So yeah, this is the function where you apply the tokenization to all the reviews in our data set. And then moving ahead, we have this TensorFlow slices function. So as when you read the data set in pandas, it stores in a data frame, and every column is stored like a series object. TensorFlow library has its own format where it requires the data to be in the form of tensors and tensor slices. And in this step, this function is basically takes care of returning our input textual data, which is tokenized from DistilBERT Tokenizer in the form of TensorFlow tensor slices. So I would recommend that you can go through this code notebook again and understand and try running each and every step so that it becomes easier to understand. Right now, we'll go ahead and split the data set into the training, testing, and the validation data set. So after splitting, we have a training size of 411 reviews. The test size is 102 and validation is also 102. So when you're working in real life data, always remember to split the data into training and testing. The testing data would never be used until the model is completely trained. And the training data, you can again divide it into like an 80-20 split or 90-10 split into training and validation data set. So here is what we divided the data set into 3 sets for training, testing, and validation. And then the last step before processing, before moving ahead, is that converting these data sets into batches. So in this block of code helps us do that. And finally, we are at a step where we fine tune a model. And the code for fine tuning is very simple here. You just have to mention the model name, which is again DistilBERT in our situation, and the number of epochs. So it's usually recommended that if you're training or fine tuning a BERT model, then any number of epochs varying from 5 to 6 is enough, because the BERT is already trained on a huge corpus of words. We are just fine tuning it to familiarize the BERT model, DistilBERT model with our own data set. And that's why number of epochs is like anything from 6 to 10 should be more than enough. Here in this main code, we are using the DistilBERT sequence classification and passing the model name to it, and the num labels parameter. So num labels is equal to 2, which indicates we have a binary classification problem. Let's say you have a 3-class classification problem where you want it to be positive, negative, and a neutral review. So you would pass the num labels as 3 over here. And if you have worked on neural network models, then you can see the optimizers is, we need to pass the optimizers, which in this case is Adam. Also, this is because the original BERT model and DistilBERT model were trained using the Adam optimizer. And we also need to define the loss, which is here the sparse categorical cross entropy loss, which we often mention when our target is in the form of 0, 1, 2, 3, or it's like a target class is integer encoded. So that's when we use this type of sparse categorical cross entropy function. And then when you have this all and you compile the model, you can see the model summary to see the trainable parameters and the pre-classifier and the classifier. So if you can see, we have the total number of trainable parameters as 66 million, and that is what we are doing here. And the code would not take like more than half an hour to run because we just have 500 around 500 samples. But yeah, if you have more data, then it might take longer time to fine tune your model. So finally, we have this model.fit, and we can see how it's this step where we also pass the training data, the batch size, as well as the validation data. So the validation data also is taken care during the training process, and we can see the accuracy for the validation as well as training data sets. And we can see as the number of epochs increases, our model is performing better. We had an initial validation accuracy of 70% when we started in the first epoch, while towards like after 5 or 6, we have a good accuracy of 97%. So this is how you can train a BERT model. And yeah, so there are also in fine tuning also there are two approaches which I would like to highlight before we open up for Q&A session. One is training all the model parameters, as we saw. What we are doing here is training all the parameters which are present in the BERT model. So whenever you run this model.fit, the weights would be, these parameters would be trained. And second is another option is freezing the layers of DistilBERT. So there's a way to freeze these layers and not allow them to change, and you can do that using the TensorFlow no-grad function. And in that case, you need to add another classification layer like a softmax layer to help the model classify the reviews. So in that case, what the DistilBERT model does is, using the preprocessing and encoding format of the DistilBERT, it generates an output, which is basically a numeric representation of the input text. And we use this input representation in the form of numbers to classify using a simple classifier like a logistic or a sigmoid function. In that case, the con of this scenario is the DistilBERT model doesn't get to see your training data. I mean, the weights are not optimized to your training data, so it might not perform as good as the fine-tuning approach, the first approach we saw in this case study. So in this case study, we are using this first approach. And if you want to explore the second approach, where you just freeze the layers of DistilBERT, and it's also a little far easier and faster to train, you can refer this blog on Towards Data Science Central, where the person has shown fine-tuning of DistilBERT for binary text classification. And once our model is trained, the last step is to validate and analyze the training loss. And it's always a good sign to have the training loss and validation loss converge or follow the same path. So yeah, here we are. And the last step is testing the model. So I think it's just 10 minutes to the end of our session. And as I mentioned, you can have a walkthrough or try running this notebook later. I believe we can open for a Q&A session. How about that, Laura?
That sounds perfect. Thank you so much, Rutuja, for sharing your expertise. NLP is such a rich subject, so I can see that several people are excited to be learning here. So there are several questions. The first one that came in refers to earlier in your talk. It's a question about parity. It says, why does it matter whether a word is at an odd or even position?
Oh, okay. So let me go back to the, it doesn't exactly matter, even if it's an even or odd position, that's fine. I mean, there's no such thing that if it is an even position, then it will do something different, or if it's at an odd position, it will do something different. But it's just the way it's easier when you encode these embeddings in a way with the help of positive or negative. So otherwise all of the encodings would be having same kind of representation. So it is easier to categorize these the position depending on the presence of even or odd numbers. And what positional embedding at the end does is that it just helps one word to understand what word is before and after it. So that's the aim of positional embeddings.
Perfect. That makes sense. Another question asks, can BERT be used to vectorize long paragraphs, for example, a movie description, and then select or maybe recommend other movies based on that content?
Yeah, definitely. That's another use case of BERT, and I would really appreciate asking that question, because there are a lot of use cases of BERT and we just have covered one. So you can definitely use it for text summarization. And yeah, since we saw in this training phase, it is basically the first task of mass language modeling. It's a semi-supervised training task, and the second one is the supervised trust. So the BERT has ability to summarize text, and as well as there is a transformer called sentence transformer, which helps you to find the similarity between two sentences and recommend whether the two sentences are similar or no. So depending on that, let's say, for example, if we have a movie review and one sentence, one review says about some movie called Matrix, and another movie or review also says some good review about the same movie Matrix, then definitely using sentence transformers, we can find the similarity score or the cosine similarity and use it for a recommendation system.
That's awesome. Yeah, that's so interesting to think about grouping text based on sort of like key words. It's really fascinating. Okay, so we have a couple, 4 more questions actually, specifically. So this one is very good. It asks, how many parameters does the BERT model have, and how much time is needed to pre-train it?
Okay, so that's an interesting question. So the BERT had around like more than 600 parameters or something, and it might have even took months for the researchers at Google to train this model from scratch the very first time. So what we usually do in industries as well is use the pre-trained model, which is also, this concept is also called as transfer learning. So in this learning, the model is trained on different data and different tasks, and you just can use that model architecture to solve your problem. So if you can just, I mean, if you Google and see, then the BERT is trained on like number of parameters in BERT. You can see, yeah, you can see, I mean, there are 110 million parameters for the base BERT. So, you know, that's a lot. And I am pretty sure that might have taken like a few days or more than months to train it. So, yeah.
Yeah. Okay. Perfect. But by using the existing architecture from that trained data, yeah, we can, we're in the clear a little bit. Okay. So the next question is, given that the training time is quite high for those models, and the fact that fine tuning adjusts all of the different weights, this person says, I expect fine tuning would take sort of timing wise, it would be comparable to training time. How is it possible to achieve such a fast fine tuning in this example?
Okay, so the example we have here in this code notebook, it took around like 15 to 20 minutes to fine tune. Another option you can do is to fine tune the model faster, which I mentioned in the second approach, right? So if you see here, we are training all the 66 million parameters here. So if you want to save your time and fine tune it faster, then there's an option to freeze these layers, meaning these the trainable parameters would be reduced to like, you know, only 700 or 769, because in that case, you would be freezing the previous layers of the BERT. So as you see, in the neural network has a lot of hidden layers. Similarly, the DistilBERT model also has many hidden layers. And in this approach where we freeze the prior layers, we would not be training or we would not be changing the weights of these previous layers. And the only weights which we would have to train are those associated with the last layer of the classification. So that's one way, but in that case, as I mentioned earlier, there can be a chance where the performance might reduce a little bit. But yeah, that's the thing you can try and error.
Yeah, absolutely.
Hope that answers the question.
Yeah. Okay, so we'll probably have time for a couple more. And again, if any questions aren't answered, then Rutuja has generously offered to answer some of them in the Q&A via text, but let's use our time here. So one of them asks, does DistilBERT recognize commonly used acronyms? I was wondering this too.
Oh yeah, the DistilBERT comes from the word distillation of the BERT model, and it's like the BERT is the elder sibling, and the DistilBERT is the younger sibling. So yeah, the BERT acronym goes for the DistilBERT as well. And I think I had a comparison of the BERT and DistilBERT models, which I can maybe show here. Yeah. So we can see here the
Perfect.
comparison of different large language models, starting from BERT. Then there's another variant called Roberta, and we have this DistilBERT here. So yeah, it comes from a method called distillation, BERT distillation. And yeah, so as we saw in this, I'll make sure to add this resource also into the Google Slides, which you can access later. And as we saw here, so since the BERT was trained on two tasks, right? The masked language modeling and the next sentence prediction. The DistilBERT was trained only on the masked language modeling and not on the next sentence task. So that's the difference. And hence the name comes the BERT distillation, because it's a slight variant of the BERT model. Yeah.
Perfect. Yeah, that's a really helpful table for summarizing.
Yeah,
okay,
I mean,
so
these days it becomes difficult to, catch up. I mean, there are so many large language models coming up in the industry. And I believe even if you are graduated and working in a company, you still have to keep updated yourself.
oh yeah, absolutely. It's ever evolving, sort of, good luck picking, just learning one and then stopping
Right.
there. No, you have to keep going. Let's see. So maybe one more question for now, and then you can answer the
Yeah,
other one in text later.
sure.
One person asks, can I use a CNN to solve these types of problems?
Yeah, so there's I mean, I can say it's a niche that you can use only CNNs for solving image classification tasks, but CNNs also can be used to solve textual problems like text classification or text data analysis. And you can do that by the CNN has those convolution pooling layers, right? So these layers can also be used to process text data. So yeah, definitely you can use CNN for solving text classification problems. Yeah.
Perfect. Then, without further ado, let's thank Rutuja. It was such a pleasure for such an informative and interesting talk. It's, well appreciated.
Yeah, I would like
And
to thank you, Laura, and the WITS team for giving me this opportunity. And yeah, I really appreciate the audience. Hope you have a lot of information. And yeah, I would be answering to your questions on the chat, definitely, for sure.
yeah, perfect. Thank you so much.
Yeah. Thank you.